last day of our short-term course on first areas of research in engineering and science. In today's morning first session, we are going to have a talk from Dr. Sanjeev Kumar, who is working as Associate Professor in the Applied Science Department of Pet University of Technology at Chandigarh. He has done his PhD from MIT Kurukshetra in the field of material science. His areas of specialization are nanowires and multifarads. He has published around 60 papers and guided PhD in these areas. He has also carried out various projects sponsored by DST, DRDO and UGC in these areas. He has also worked as faculty in the Punjabi University Patiala before joining Tech University of Technology at Chandigarh. So I request him to kindly highlight the upcoming research areas in nanotechnology and material science.
Yes, ma'am. Thank you very much, ma'am. So first of all, I would like to thank Dr. Poonam Sayal for giving me this opportunity to share my research work with all of you. First of all, good morning to all of you. Can I start? So the topic of my talk is today. Today is areas of research in nanotechnology and material science. So can you imagine or can you judge what is this photograph? So contact तो हमारा नहीं होगा, मैं डायरेक्ट ही बता देता हूँ आपको. So actually it is basically a photograph of our tongue. So actually your tongue is like this. So when you view it through electron microscope, so you can see that your tongue is like this. That is having so much bacteria, saliva particles, and so many things. And this is the second one. That is a crack in a steel. This is a mosquito photograph. This is a human hair, and from this photograph you can imagine that the thickness of the human hair is around 60 micron. It is 60 micron. Can you imagine what is this? This is a thread in a needle. This is a spider, and this is a cross-sectional view of a leaf. So before going to this topic, basically these all are electron microscope images. So I will also cover this topic later on, but first one is that the main area is the nanotechnology. So there is one very important phenomena in nanotechnology that is known as quantum confinement. So as per the quantum confinement, basically the energy levels, they get discrete. In the bulk material, they are basically continuous, but when we make the nanoparticles of the same material, then those energy levels, they get discrete. And this phenomena is called quantum confinement. So, from this slide, I want to tell you that suppose if you have a material which is bulk in nature, means having 3 dimensions, and it has some free electrons, then the electrons can move all in any of the 3 dimensions, like along x-axis, along y-axis, or along z-axis. Suppose if I removed one of the dimension, like the first part in this slide, that is known as thin films. So in this case, your electrons can move only along 2 directions, either along x-axis or either along y-axis. So we have restricted the motion of the electron along z direction. We have restricted the motion of electron along z direction. So in thin films, your electrons can move only along 2 dimensions. So your electrons, they get confined in one direction, that is the z direction. Suppose if I remove the 2 dimensions, that is from the bulk Or in the thin film, if I remove one more dimension, then I have a sort of wire. And in the wire, your electron can move only along the one direction. Suppose if your wire is along x-axis, then your electrons, they can move only along x-axis, either in forward direction or in backward direction. They cannot move along y or z direction. So your electrons are confined in two directions. And suppose if I remove the third dimension also, means you have a dot. So in that case, your electrons, they cannot move. They get restricted. So they are confined in all the three directions. They cannot move in either of the direction. They get restricted. So this phenomena is very important, and it is known as quantum confinement. And suppose if you have a material, let us say copper, you have a bulk material, then you deposit a thin film of the copper, and then you make a nanowire of the copper, and you have some nanoparticles of the copper. Then all the four things, that is the bulk, thin film, nanowire, and nanoparticles, all of them, they will show different properties. And all the properties you can describe on the basis of the movement of the electrons, because you have restricted the electrons in different types of structures in different manner. So that is the thing that I want to say you. That is, in the case of a suppose bulk semiconductor, you have a valence band and a conduction band, and both of them, they are separated by some particular energy band gap. But in the case of quantum dots, these bands are not continuous. They get converted into discrete energy levels. They get converted into discrete energy levels, and because of these discreteness, you can play with the different properties of the particles, because you can transfer the electrons as per your requirement to the particular energy level. You can move the electron as per your requirement, and because of this type of discreteness in the energy levels, they are also showing the different optical properties. Suppose if I have a material whose color is yellow in the bulk, but if I made the nanoparticles of the same material of the different sizes, then they will show the different colors. Like this is a slide which is describing the cadmium selenide nanoparticles. In this photograph, along the x-axis, you can see the size of the particles that is dispersed in some solvent, that is varying from 4 nanometer to 2 nanometer. And when you allow to fall the UV light on the dispersion of these nanoparticles in some solvent, they will show the different colors. And this is because of the size, the smaller size, as smaller as you are going, the colors are going to be different, and that is related to your quantum confinement effect. Now, this is a very important slide, that why properties of nanomaterials are different. There are two main criteria on the basis of which we can tell that why these nanomaterials are different from their bulk counterparts. First one is the increased surface area, and second is the quantum confinement effect, which I had already described to you people. So the first one, that is very important, that is the surface area. So suppose if I have a spherical particle, and then I want to take the surface area to volume ratio. Suppose the radius of the sphere is r, then the surface area is equal to 4 pi r square, and the volume is equal to 4 pi r cube by 3. So if you take the ratio of this surface area to volume, then the ratio is 3 upon r, where r is the radius of the particle. So suppose I created a particle whose radius is 1 meter, then this ratio is 3. If I make a particle whose radius is 1 centimeter, then this ratio becomes 300, because 1 centimeter is equal to 1/100th of a meter. So this ratio becomes 300. So if I make the particle of the radius 1 micron, 1 micron means 10 to power minus 6 meters, then this ratio becomes 3 into 10 to power 6. And what we are talking about? We are talking about the nanomaterials. So the nano means 10 to power minus 9 meter. So 10 to power minus 9 meter, if we make a particle whose radius is 10 to power minus 9 meter, then the surface area to volume ratio for that particle is 3 into 10 to power 9. Now what it shows basically? In the next slide, I will show you. In this slide, you can see along the x-axis you have the particle size in nanometers, and along the y-axis you have the percentage of atoms surface. So you can easily see that as the size is going on increasing, the number of atoms on the particle on the surface, the number of atoms in the particle on the surface, that is going on decreasing, right? But the number of atoms in the bulk, that is going on increasing. There are two curves. One is showing bulk atoms, second is showing surface atoms. So as you increasing the size of the particle, the surface atoms are going on decreasing, but the bulk atoms are going on increasing. But if you decrease the size of the particle, the bulk atom is going on decreasing, but the surface atoms are going on increasing. It is a very important concept. So in the case of a particle, suppose if it if you have a particle and its size is very small, then the more number of atoms they are lying on the surface in comparison to the number of atoms lying in the core. So when the number of atoms lying on the surface are more, then its reactivity will be more, its optical property will enhance, its electrical properties as well as all other properties, they will be different as compared to its bulk counterpart. Because if we take the same material in the bulk form, then the more number of atoms they are lying in the core, which are not directly interacting with whatever the field you are applying, whatever the external force you are going to apply, right? So it is a very important thing that in the case of nanoparticles, the number of atoms on the surface is more in compared to the core of the particle. So there are basically two different approaches for the fabrication of nanomaterials. One is known as top-down. So top-down means start with the big material and cut away material to make what you want. So I will give you some examples of that later on. And the second technique is bottom-up. That is building what you want by assembling it from small prefabricated units such as atoms or molecules. So out of these two techniques, that is the top down and bottom up, basically bottom up is more preferable technique because it is cost effective as well as more result oriented. So this is the second slide. Before describing this slide, I want to tell you that suppose if you have an optical microscope and you want to view some small particle through that optical microscope. I think you all know about the optical microscope. So the magnifying power of the optical microscope is only 2000 times. The magnifying power of an optical microscope is 2000 times, through which you can see the red blood cells, right? And the size of a red blood cell, the average diameter of the red blood cell is 7 micron. Micron is 10 to power minus 6 meters. Your hair, that is the human hair, is 60 micron thick. That is 60 into 10 to power minus 6, right? So if you want to see the nanoparticle whose diameter is in nanometers, then you cannot use the optical microscope. It is very difficult. It means there is no means through which you can see the nanoparticles through optical microscope. So to see the nanoparticles or the nanomaterials, that what is the size of that particle, what is the shape of that particle, you have to take the help of the electron microscope. So how electron microscope is different from that the optical microscope? So in the case of optical microscope, you are using the light. you're using the light which falls on the particle and get reflected back, and you can view the image of that particle. But in the case, there is a limitation. What is the limitation? The limitation is this: the wavelength of the visible light which you are using in the optical microscope is limited. It is lying from 4000 angstrom to 7000 angstrom. And out of this particular region, we usually use the yellow color, that is around 5500 angstrom or 550 nanometer. So there is one important thing, that the resolution of a instrument is inversely proportional to the wavelength you are using. So if you decrease the wavelength, then the resolution of the instrument will increase. So there is a very fundamental concept behind this. I think all of you know about the de Broglie wavelength. So de Broglie wavelength, that is telling you that every material in the world has dual nature, particle nature as well as wave nature. And as per that de Broglie wavelength, lambda is the wavelength. You can write your lambda is equal to h upon mv. H is the Planck's constant and mv is the momentum of the particle. M is the mass, v is the velocity. So lambda is equal to h upon mv. So de Broglie basically linked the wave type of nature and the particle type of nature together by the Planck's constant h. And he gave the hypothesis that both the nature of every particle exists simultaneously. That is the wave nature as well as the particle nature. All of you have the wave nature. But what is the problem? The problem is that the mass is large. Lambda is equal to h upon mv. If mass is large, wavelength will be very, very small because lambda is inversely proportional to mass. But if you take, instead of a human being, an electron, electron's mass is 9.1 into 10 to power minus 31 kg. So you will get an appreciable value of the wavelength. So that means that electrons, they can act as particle as well as wave. So in these instruments that I am showing on the slide, can you please? This is known as scanning electron microscope. So in this instrument, we will use the electrons instead of light. And now we are considering that electrons are behaving as a wave. So if they are behaving as a wave, then the energy of the electron as per wave nature, that becomes E is equal to h nu. E is equal to h nu, where nu is the frequency, h is the Planck's constant, right? And all of you know that frequency is inversely proportional to wavelength, right? So E, you can write it as E is equal to h into v upon lambda. V is the velocity of the particle with which electron with which it is moving. So energy is inversely proportional to lambda, right? So when you decrease the lambda, energy will increase, or if you increase the energy, lambda will decrease. Both means, just I am saying you. So if a particle with higher wavelength, its energy will be less, but the particle with lower wavelength, its energy will be high. As in the case of photons, you can see that for a blue color photon, frequency is high as well as energy is high, but the wavelength is small. But for a red color, wavelength is high, but the energy is small. So same concept is applicable to the electrons in this case. So how you can increase the energy of the electron? Because you want to decrease the wavelength of the electron. So if you decrease the wavelength of the electron, the resolving power of the instrument will increase. So how you can increase the energy of the electron? You know that if you try to move an electron between the applied potential of 1 volt, then its energy is 1 electron volt. If you increase the potential, then its energy will also increase. If you apply the 100 volt in a vacuum, then it becomes 100 electron volt. If you apply 1000 volt, then it becomes 1000 electron volt. So in this manner, by applying the potential, you can increase the energy of the electron and correspondingly decrease the wavelength of the electron. So if you decrease the wavelength of the electron, you can increase the resolving power of the instrument. So this is a very important, very important concept which revolutionized the field of the nanomaterials. Because if we don't have these kind of electron microscopes with us, we cannot further progress in the field of nanotechnology, because we will not be able to see the particles, what is their shape, what is their size, right? So it is a very important instrument. And further in this instrument, even though you can tell that suppose if you have a particle, that what type of impurities it has, or what is the composition of that particle, each and everything you can tell with this instrument, that is known as scanning electron microscope, right? And the magnifying power, as I told you, that for an optical microscope it is only 2000 times. But can you imagine what is the magnifying power of this instrument? Its magnifying power is 2 lakh times. It is 2 lakh times. So you can see easily the nanoparticles. But nowadays, we have one further improved version of this electron microscope, that is known as transmission electron microscope. This one is the scanning electron microscope, and this one is the transmission electron microscope. So in this microscope, you can increase the magnifying power up to 4 lakh times. In the scanning electron microscope, the magnifying power is up to 2 lakh times. But in the transmission electron microscope, you can increase the magnifying power up to 4 lakh times, right? But the constraint of this particular microscope is that you have to make a very thin sample through which your electron beam can transmit, because its name is transmission electron microscope. So you have to transmit the electron beam through the material. So in my opinion, these two instruments, that is scanning electron microscope and transmission electron microscope, are very important instruments without which you cannot progress in the field of nanotechnology. So whatever the thrust areas nowadays they are emerging in the field of nanotechnology, all of them, they will use these two instruments. So second, I will discuss the different major areas later on, but the second one is the material science. So what is material science? So material science is a discipline which primarily concerned with the research for basic knowledge about materials. Each and everything is a material. Like what you are seeing on the screen, that is a material on which you are getting the projection of from the computer. You are sitting on chairs, that is again a material. So each and everything is a material. So the main properties of the materials, the main concern about the materials is structure, properties, and processing. So material science deal with these three things: structure, properties, and processing. But what materials engineering do? It converts the materials into products so that a common man can use that product. So material engineers are very important, that they convert the materials into products. So we have four basic elements: structure, property, processing, and further performance. So structure, what is structure? So at the subatomic level, all of you know that you have in the atom you have a nucleus surround, and the electrons are moving in the orbitals, particular orbitals around the nucleus. And at the atomic level, you have different ions, different atoms. They are in some particular means at some particular positions, arranged in a regular fashion. Those are known as crystalline materials. If they are not arranged in a regular fashion, that is known as amorphous materials. So the mechanical property. So now I am discussing the different properties the materials they can show. That is, the first one is the mechanical properties. So what is mechanical property? That reflects the relationship between the material response to an applied force or load. So what are those properties? Strength, hardness, ductility, stiffness. Second is electrical property, that deals with the response of the material to the applied electric field. So what are further parameters? Electrical conductivity, dielectric, constant. Thermal property, the response of the material to the application of heat, that is heat capacity and thermal conductivity. So these properties, they are very important, which decides the usability of the material. Magnetic properties, the material response to the application of magnetic field, that is magnetic moment, magnetic permeability, that like I am using the computer. So in this computer, the data storage is basically a magnetic hard disk in which you are storing the data. So this is again a material. Optical properties, which the response to the electromagnetic radiation. So basically your light is an electromagnetic radiation. So it is a refractive index, reflectivity. These are the main concern regarding the optical property. The last one is the deteriorative property, that is related to the chemical reactivity of the materials. That is also very important property, like your iron that picks up the rust. So how you can avoid that one? By coating some particular material on it or by some other means. So I'm not going into this one. Now I'm directly going to the type of materials. So basically we have different types of materials like metals, ceramics, polymers, composites, advanced materials. Now in the advanced materials, we are talking about these thin films and the nanomaterials. So before going into the material, I want to tell you the important property, that is the structure, because each and everything is made up of atoms, and further atom is made up of nucleus. That nucleus is made up of protons and neutrons, and the electrons are surrounding the means they are moving in some particular orbitals surrounding the nucleus. So it is very important to know what is the structure of the material. First of all, is it crystalline in nature or is it amorphous in nature? Because the crystalline structure tells you that all the atoms, they are arranged in a very regular pattern. But in the case of amorphous material, the atoms, they are not arranged in a regular pattern. So that is very important. And further, these crystalline materials are divided into 14 Bravais lattices. I think all of you know about the simple cubic, body-centered cubic, face-centered cubic, hexagonal, rhombohedral, orthogonal, trigonal. So there are basically 7 crystal systems which are further divided into 14 Bravais systems. So first of all, it is very important that if your material is crystalline in nature, that what is the structure of your material. So to know the structure of the material, the very important instrument, first of all, the very important technique, that is known as X-ray diffraction. X-ray diffraction. I think all of you know about the Bragg's law, which tells you that how X-ray diffraction acts. But before going into that one, first of all, I want to tell you that why we use only X-rays to determine the structure of the material. Why we are not using this visible light to determine the structure of the material? Because the technique is X-ray diffraction. So for the diffraction to occur, the important thing is that the obstacle size through which the light will bend, its size should be comparable to the wavelength of the light. Then your diffraction will occur. So what we are going to study, we want to know what is the structure of the material. So in that material, because your atoms, they are arranged in a regular pattern, and the distance between the atoms, that is the interatomic distance, that is very, very small. That is very, very small. So if your interatomic distance is comparable to the wavelength of the light, if your interatomic distance is comparable to the wavelength of light, that is the X-rays, that is basically X-rays, then your diffraction can occur. then your diffraction can occur. So that's why we use only the X-rays to study the crystal structure. We cannot use the visible light or the ultraviolet light or the microwaves. So we can use only the X-rays. So this is the instrument that we use for the X-ray diffraction. So in this instrument, we have first the X-ray generator, which generates the X-rays. Second thing, those X-rays should be monochromatic in nature, means they have the single wavelength, and when they fall on the material, then they get diffracted in different directions. So there is one detector which detects the diffracted X-rays, and that will give you some pattern. I will show you some pattern of a particular material like this. So this is the Bragg's law. What it is telling you? It is telling you that lambda is equal to 2d sine theta, where theta is the angle, that is basically the red lines, they are those are the X-rays, and the black lines, those are the planes in which your atoms are situated, and the distance between the two planes is small d. Distance between the two planes is small d, that is known as interplanar distance. That is known as interplanar distance, and red lines are the X-rays that get diffracted through these planes inside some material. So what Bragg's law says, that is lambda is equal to 2d sine theta, where theta is the angle, the X-rays that are making with the planes, d is the interatomic spacing. So if your crystal is obeying this Bragg's law, then you will have some X-ray diffraction pattern. But if it is not obeying this law, it means your material is amorphous in nature. It is amorphous in nature. So I think you can see a plot below it. Along the x-axis you have intensity of X-rays. Which X-rays? Which get diffracted from the material. And along x-axis you have theta value. Along y-axis you have intensity, and along x-axis you have theta value. So here you have two plots. One is for calcium titanate and the second for strontium titanate. These are two ceramic materials basically, and you can see the difference between two. First of all, I want to tell you that as per this Bragg's law, you have different theta values. Like in this plot, there is a peak around 32 degree. There is another peak around 40 degree, and then around 46 degree. Right? So what these peaks shows? These peaks shows the planes, the different types of planes your material have. Where this in this Bragg's law, you can see in the subscript of D, there is a value that is known as HKL. These are known as Miller indices. If you can remind your basics of the solid state, that is HKL. These are the Miller indices, which shows that a particular plane. Suppose in this case you are at the first angle, that is around 33 degree, you have a peak. One is in green and the second one is blue. So the intensity of green is high, but the intensity of blue is very low. So what is the reason behind that? The reason behind that, it is the blue one is for calcium titanate and the green one is for strontium titanate. So both of these peaks corresponding to particular plane. But why the intensities are different? Because the intensity is high, that means the number of atoms in that plane are more. Because if the number of atoms in that plane are more, they will diffract more X-rays. But if the number of atoms in that plane are less, then they will diffract less X-rays. So what it shows, that in the case of calcium titanate, the number of atoms in this particular plane are less in comparison to strontium titanate. Yeah, there is one problem, that strontium titanate I have written in red, but the peaks are shown in green. So don't misinterpret. That is basically for strontium titanate, right? But on the second peak, that is around 40 degree, you can see that for calcium titanate now the intensity is more, but for strontium titanate it is less. So this corresponds to this another plane oriented in different direction, because the first one is is giving you the value of theta around 33 degree, but this is giving you the value around 40 degree. So in this case, the calcium titanate intensity is more, means the plane corresponding to calcium titanate has more number of atoms in comparison to strontium titanate. So this is the view of an X-ray diffraction pattern. So this is a very very simple view. Simple, I can say that that you can easily judge that which peak corresponds to which material, and further which peak corresponds to which particular plane of that material. So there are different complex materials in which you can observe 50 peaks only in this region, that is from 25 to 50 degree. So to analyze those kind of materials, it is very difficult. But nowadays we have such a technology that we can easily judge that how many number of peaks it has and what type of structure it has. So from these peaks in the X-ray diffraction pattern, you can easily tell whether your material is cubic in nature, its structure is cubic, or it is hexagonal, it is rhombohedral, or some other thing. Because if it is cubic, suppose it is showing 3 peaks, but suppose if it is rhombohedral, then it will show 5 peaks. So different structure will show you different number of peaks, and there is a ready-made data available for standard data available for all kind of materials. So you can compare the data of your material with the standard one and easily tell that what different things you are observing in your material. So these are some applications of X-ray diffraction technique, which is very, very important if you want to work in the field of material science or in the field of nanotechnology. This X-ray diffraction technique is very, very important. So first one is the differentiation between crystalline and amorphous materials. So if you are getting the peaks in the X-ray diffraction pattern, that means your material is crystalline. But if you are not getting any peak in the material, that means your material is amorphous. So what is the difference? Crystalline means your atoms, they are arranged in a regular pattern, but in the case of amorphous, they are not arranged in a regular pattern. That's why you are not getting any peak. You are just getting some hump. Second is determination of structure of crystalline materials. You can easily determine whether your material is, first of all, it is crystalline, then what type of crystal it has. Is it cubic? Is it rhombohedral? It is monoclinic? What type of crystal structure it has? Third one is determination of electron distribution within the atoms and throughout the unit cell. This is a very important parameter. Then you can easily determine the electron distribution within the atoms as well as throughout the unit cell, which will further help you to describe the optical and electrical properties of that material. Fourth one is determination of orientation of single crystals. So basically, single crystals are those crystals in which you have no grains. You have a single grain. That means the whole material is arranged in a particular manner. So single crystals are very important, but it is very difficult to grow the single crystals. So that's why we are moving towards the polygrain materials. So they are giving the similar properties, but not like that of the single crystals. Then from these X-ray, you can easily tell what is the grain size or what is the strain. Even though if you are dealing with the nanoparticles, you can tell what is the average size, and then you can compare with that of the electron microscope images. So now I am going to some of the research work that is carried out by me in my lab or during my PhD. So first one is the template synthesis, a membrane-based approach for synthesis of nanowires. So using this technique, we have grown nanowires. For the growth of nanowires, we took some membranes. Membranes means some polymeric material which is having pores. So these are the polymeric materials. These are basically the electron microscope images of that polymeric material. And you can easily observe that there are pores in that material. So in the first image, the pores are very far apart from each other, but in the second one, some of them, they are overlapping on each other, and in the third one, the overcrowding is so much that the overlapping is also very large. So we can use these type of membranes for the synthesis of nanowires. So what we'll do, so this is the technique that is known as template synthesis. So first of all, we took a polymer and then we irradiate with it ion beam. Ion beam means heavy charged particles. When they hit the polymer, they penetrate the polymer, and when they penetrate the polymer, they create some reactive sites in the polymer, which you can easily etch using the chemical, and those sites they get converted into pores. Then on the polymer film, you can deposit conducting film on one side of the polymer and other side remain as it is, and then you can deposit some material inside the polymeric membrane, and after that you can dissolve that polymer and you will get the nanowires. So I will show you some results of the nanowires we have grown. So these are the copper microstructures we have grown using this technique. These are some cobalt nanotubules we have grown using this technique. So you can easily observe in the second micrograph, that is the cobalt nanotubules, that they are basically tubes, not the solid rods. Then we have grown cobalt and nickel nanostructures, and these are very important structures because you can use these type of nanowires for magnetic data storage. Then we have grown by a simple technique some polymeric tubules, that is a conducting polymer. That means they are flexible in nature, but as well as they are conducting in nature. So you can use that in flexible electronics. These are again some of the micrographs. So I am not going into this one. This one is important. So in this micrograph, basically I want to show you that we have grown the copper selenium heterostructures using this technique. So copper is a metal, but selenium is a semi-metal. Copper is a metal, selenium is a semi-metal, so the properties are different. Electrical properties of both the materials are different. So half of the material is copper and half of the material is selenium. So so at the junction of the metal and semi-metal, there is some resistance to the flow of electrons. And because of that, when we measured the IV characteristics of these type of heterostructures, then we observed that they are showing some sort of resonant tunneling behavior. Because the size of these one is very, very small, so by using a small size, you can increase your chip, means the number of like capacitors, resistors, or whatever in which way you want to use these wires, you can increase a number of components in a very small area. So these are the silver iodide nanowires. So how I studied these one? First I grow the nanowires, then I took those nanowires to the electron microscope. First of all, I studied that what is the size of the wire, what is the diameter of the wire, and after that we studied the X-ray diffraction, that they are crystalline or not. So after studying, yes, they are crystalline in nature. Then we studied their elemental composition, that suppose I have grown silver iodide wire, how much silver is there, how much iodine is there, and after that we studied the UV visible absorption. Means this is a semiconductor material, so when you allow the visible light on this material, it will absorb some of its wavelength. So from that we can tell that what is the band gap of this material. This is again for silver bromide. So first of all we grow the wires, then we took the X-ray diffraction, which shows, yes, that it is crystalline in nature. Then we took the EDX, which tells that silver is present there, bromine is present there, means it is really silver bromide. And then we took its optical absorption, and from that we find that what is the band gap of this material, means what energy you require to transfer the electrons from valence to conduction band. So after that we have used instead of polymeric membranes, now we are using these anodic alumina membranes. So what is the advantage of these? That the pores in these membranes, they are very much regular in comparison to the polymeric membranes. because in those membranes the pores are randomly oriented and sometimes they are overlapping each other, and because of that you will not get a uniform distribution. But in this case the pores are very much uniform, even though you can get the height length of the wires. So I'm not going to this one. Yeah, this is the basic setup to grow these type of nanowires. It is a very simple setup where that you require one potentiostat and then a simple cell, and this cell is known as 3 electrode cell. So basically what we are doing the electrode deposition, simple electrode deposition. But in which material we are doing the electrode deposition? We are using the membranes in which we have the pores. In those pores the material will deposit, and after that you can dissolve the membrane and you will get the wires. So this is the simple cell setup that we are using, and on the right hand side you can see that you have the membranes. The first image is showing that we have coated a silver paste on one side of the membrane, and then we electrode deposit the material in it, and after the electrode deposition the membranes are looking like this. Now you can dissolve these membranes. So I am going to the second example of using this technique, that is a gold nickel nanowires, that is basically alloy nanowires. So we have used the electrode deposition process, but in this case what we have used because gold is deposited at a different potential and nickel is deposited at different potential, so we have to use a periodic potential type of voltage supply. So by using that we have grown these wires. Now you can see the wires in the template. We have not dissolved the template, but you can see the wires that are inside the template. This is a cross-sectional view of the membrane. So we have confirmed that yes, these are gold and nickel. So how we confirm that? This is the second photograph I am showing to you. That is the scattered electron, backscattered electron image, in which you are getting that some of the portion is lighter and the some of the portion is dark. Some of the portion is bright and the some of the portion is dark. So the dark portion is gold and the brighter portion is nickel, because the atomic number of the gold is more in comparison to nickel. So it will reflect more X-rays more electrons in comparison to nickel. So that's why the gold part is looking dark, but the nickel part is looking bright. So it confirms that gold and nickel is there. Then we did the XRD, which further confirms yes, it is a crystalline material and it is showing the both peaks of gold as well as nickel. Then we studied its magnetic properties, because nickel is a ferromagnetic material. And this is a further study which shows that only 6% of nickel is there, but 93% is gold. Even though the 6% nickel, it is showing very weak ferromagnetic properties of these gold nickel nanowires, which can be used for data storage purposes. This is again for the copper nickel nanowires. So first we study with the gold nickel nanowires, but gold is so expensive, so we turn to the copper nickel nanowires. But again, it is easy to grow these type of nanowires. And now what we observed in this case, that it is showing enhanced ferromagnetic behavior in comparison to gold nickel nanowires. So these are more usable in comparison to gold nickel. And these papers are published in very good journals. Second, we try instead of nickel the cobalt one, and in this case now it is a multi-layer. In this case you can easily see that in the nanowires you can see there are layers. One corresponds to copper, another corresponds to nickel, and below this SCM image, electron microscope image, you can see what is the distribution of cobalt and copper. So it is showing cobalt is around 15%, copper is 17%, but the aluminium is 62%. So what is aluminium? So aluminium is basically the membrane, the anodic alumina membrane we are using for the deposition of these type of wires. So these are again some of the wires we have grown using this technique. This is again one more semiconductor, that is bismuth ferrite. We have doped with the gadolinium and we studied the X-ray diffraction. Now in this case I want to show you that in the graph which is in between the which is the centered one, the blue curve is showing the X-ray diffraction for pure bismuth ferrite, but the upper one, that is in red color, it is showing the 10% gadolinium doped bismuth ferrite. So here you can easily see that in the case of blue one, that is the pure bismuth ferrite, there are two peaks. But in the red one, the two peaks, they get merged into a single peak, almost get merged into a single peak. So it shows that because of the gadolinium doping, your structure is completely changing. So it is the importance of the X-ray diffraction in material science, that you can change, change the structure by doping the different materials, but how you can investigate whether it is changed or not. So you can see that by using the X-ray diffraction. So these are the dielectric properties, that this bismuth ferrite is a ceramic material and it is a very good dielectric, but even though it is showing some magnetic properties. So this can be easily used for further data storage purpose. So I am not going to this next one, so I am going to the one more interesting area. Basically the topic is the different, the second one is the dilute magnetic semiconductors. So we have used two type of materials, that is zinc oxide and zinc sulfide. Why we use these two materials? Because they are less toxic in comparison to other materials, as well as easily available. And if you want to prepare these one, the chemicals are not so costly. So you can easily prepare by using the simple methods to grow these kind of these materials. So what is the magnetic semiconductors basically? So we are using the semiconductors for our electronic industry, but for the data storage purpose, initially we started from the floppy disk, then the magnetic data. Nowadays we have external data storage, pen drives, each and everything. But the recording material is again a magnetic. For the processing of the electronics, you required semiconductor, but for the storage of the data, you required the magnetic material. So if we combine the two one, that is the semiconductor and magnetic, those are known as magnetic semiconductors. And that is very, very important, because if you can achieve both the properties, that is semiconducting nature as well as magnetic nature in a single material, that will enhance the storage capability of the material. So nowadays, we have one more important field that is coming into the picture, that is known as spintronics. So spintronics is basically, first of all, what is electronics? Electronics is because of the electron motion, the science that deals with the motion of the electron. And what is spintronics? The spintronics is the science which deals with the spin of the electron. I think all of you know that electrons have two types of spins, up spin and down spin. So if you can control the spin of the electron, then you have to apply less amount of voltage to get what you want from the electron motion. Otherwise, you have to apply a large voltage for conduction purposes or for some other purposes. But in this case, if you get a control over the spin, that you allow only the upspin electrons to move and the downspin, you can restrict those one, then you can increase the efficiency of your particular device. That is the important thing. So this is a very important field, that is spintronics. And what is the advantage of this? That the power requirement is low, but the functionality of the material will increase. That it can do so many things in the same phase of the material. That means its processing speed will increase. And people are working a lot in this particular field, but still they are not able to get some commercial device based on these spintronics. So So I am going to the work what we have done in this field. Now in this case, first I will start with the XRD. You can see the XRD peaks. This is the nickel doped zinc sulfide material. So zinc sulfide is cubic in nature, so you can see the XRD. The second micrograph is showing the Raman spectroscopy. I think all of you know about the CV Raman, who gave this Raman spectroscopy effect. And nowadays, this is a very this particular technique is so much important. Then it can tell you whether your material is, what type of structure it has, what type of bonds it has, how they are moving, how you can sense the motion of those bonds, each and everything that you can tell using the Raman spectroscopy. So this is the Raman spectrograph of these particles, and then after that there are three simultaneous graphs. Those are the photoluminescence, which is showing that if you have grown the material, that what type of defects that material can have. And in the last, I am going to this transmission electron microscope image. So in that image, you can see some circles, white circles. Those white circles that are showing you that your particle, what is the particle size. And I think in the left in the left of this micrograph, at the end, you can see there is a bar which is showing 5 nanometer. So which shows that your particle is of the 5 nanometer. 5 nanometer means 5 into 10 to power minus 9 nanometer. So what is the human hair width? It is 60 micron. And 1 micron is equal to 1000 nanometer. 1 micron is equal to 1000 nanometer. Right? So basically, these semiconducting materials, after doping with some magnetic materials, they are showing the magnetic properties also. So by using this technique, we have basically get the two properties, that is semiconducting as well as magnetic, in a single phase material, and that will increase the efficiency as well as the data storage capacity. This is for cobalt and nitrogen doped zinc oxide nanostructures. So I am going to the next one, that is important field I want to discuss with you all. This all work we have done in our lab. So yeah, this is the one very important field that is known as multiferroics. So in this case, now again we are going to submerge two different properties. Now what are those different properties? One is ferroelectric and second is ferromagnetic. One is ferroelectric and second is ferromagnetic. And for ferromagnetic properties, your outer shell orbitals, they should be unfilled, means partially filled. But for ferroelectric properties, they should be completely filled, right? For ferroelectric properties, they should be completely filled, but for the ferromagnetic properties, they should be partially filled. But how we can get both these properties in a single material? Because if you have a single material, so in that case, your outer shell may be partially filled or may be completely filled. But there is a technique through which we can get these two properties in a single material, and those are known as multiferroic materials. So in the case of magnetic materials, when you apply the external magnetic field, you have some magnetization in the material. And in the case of ferroelectric materials, if you apply the electric field, then you have some polarization in that material. But if we combine both of these properties in a single material, then if you apply the magnetic field, you can control the polarization of the material, or if you apply the electric field, you can control the magnetization of the material. So it means more controls now in your hand. So that improves the efficiency. But second thing, it is very rare. It is very rare to combine the two properties, because I already told you that in the case of ferroelectric, your D shell, that is the outer shell, that should be completely filled or completely empty. But for ferromagnetic, it is partially filled. So there is a one important material which is used these days for this multiferroid, that is known as bismuth ferrite. Yes, now I am showing you that first one is the ferromagnetic random access memory. So what we are using in our hard disk. So your hard disk is a basically ferromagnetic random access memory that based on that you apply the magnetic field and you can control the magnetization. And nowadays we have ferroelectric devices in which you can apply the electric field and can polarize the material. So in this manner you can store the data. Now how you can store the data? Suppose at a particular applied electric field you reach to the saturation value. From that saturation value you cannot come towards the lower value unless you can apply, you have to apply the field in the opposite direction. So that is a permanent data storage. So if you apply the electric field in the opposite direction, then you can reverse the polarization. Otherwise it will remain as it is. But now what we are doing, we are going to combine these two. We are going to combine these two, that with the application of electric field you can control the magnetic properties, and with the application of magnetic field you can control the electrical properties. So basically that will increase the efficiency as well as the data storage capacity in the form of multiple state memories. So this is one particular material, that is the bismuth ferrite, but nowadays it is almost get saturated. People are searching for the new material because it is not giving the required properties for device fabrication. So in this case you can see the structure. The red atoms, they are of oxygen, and the blue atoms, they are of bismuth, and the yellow one, that is of iron, at the center of the cube. It is exactly at the center of the cube, which is responsible for magnetic properties, and bismuth is responsible for the electrical properties. So I am not going into the details of this one. Yeah, now I am I think time is almost over, ma'am, or I can talk for 5 minutes. So I will just tell you some of the thrust areas nowadays people are working. So DRDO, I think you know about the DRDO, that is Defense Research Development Organization. So they are searching for the materials which are radar absorbing materials. So if your plane is moving in the sky, then if the enemy is targeting his radar, then you should coat some material on the plane that will absorb that radio waves. So the enemy will not get the reflected rays. Second is the quantum cascade lasers. Nowadays people are using displays with carbon nanotubes and the powerful lasers that is having power 100 kilowatt, because you can use these type of lasers for cutting purposes. Even though DRDO wants that you can use these type of lasers and you can target the enemy vehicles with these type of lasers. So these are basically the DRDO demands. But in my opinion, the important thing is the energy and water, because our population is going on increasing and increasing. So the main areas of research, they should include the energy and water. That is, first one is the recycling of the water, that how you can use the recycled water, and the second is the energy. Energy is very, very much important. And among the various type of energy, the solar energy is very much important for us, because in the India, the sun is available throughout the year in comparison to the Western countries. But what is the problem is this, that if you are using some sort of solar photovoltaic cells, they can show very good efficiency up to 42 degree. But beyond the 42 degree, their efficiency is going on decreasing. And in summer, in northern India, the temperature rises up to 50 degree, 48 degree, 50 degree. So in that temperature, the efficiency of these photovoltaic cells that decreases. So it is a very important area, that how we can increase the efficiency of these solar cells in the high temperature range, that is around 48 to 50 degree. So this is a very important area in which the people can work. Second one is the batteries. So because this we are running our cars, our vehicles on petrol and diesel, but maybe in future there is a scarcity of these kind of petrol and diesel, so we have to move towards the batteries, rechargeable batteries, which can run your vehicles. So it is a very important area, and the developed countries, they already developed some cars which are using these kind of batteries. So you can move up to a particular distance, and after 80 kilometers you have to recharge the battery, and again you can move further. So that will also decrease the pollution. By using the battery vehicles, you can decrease the pollutions. One important thing is that is thermoelectric materials. That every machine you are using, it is generating some sort of heat, and that heat is wasted. So if we use that heat to further convert into some sort of usable energy, so those materials are known as thermoelectric materials. And nowadays people are searching for these kind of materials which can convert this waste heat into the useful energy. So these are particular main thrust areas that you can opt for the common human being, so that everybody can use this kind of research. So these are very important research areas. That is energy. So this I want to show you that the night view of the whole of the earth. So in this you can easily identify where India is. So much energy is required. These are some good books on the material characterization techniques and the nanomaterials. They are easily available on the internet. Some of them, they are free of charges. And these are the facilities available in my lab, that we have different types of furnaces, box furnaces, ferroelectric loop tracer, then we have LCR meter, some ball mill units, spin coater, hydraulic press. So these small facilities I have in my lab. So through using these facilities, we are working in some particular areas. So with this, thank you very much. Thank you.